Hello all, I'll explain problem E, arena. So briefly, what does the problem say? That you have an arena where there are n people initially, and there are a number of iterations. In each iteration, suppose there are n people in that particular iteration, every person will inflict a damage of 1 on every other person. So for example, if initially you have 5 people, then in the first round everyone will inflict a damage of 4 on everyone else, because you are not inflicting a damage on yourself. So, for example, if someone has an initial health of 18, then after this round his health will become 40. After every round, if any player has a health which is less than 1, suppose in the first round itself you have 5 players and the first one player had a health of 3, then since that damage of 4 will be inflicted, his health will become -1. So he will die in this round, and the number of participants will, and a new iteration will be started, and the number of participants in that new iteration will also change. Because of that, the damage which is being inflicted now will also change. Okay, and you have to find what all permutations of initial healths are possible. So you are given a variable x, and that means that every element has a health between 1 and x, and you have to find all the permutations of healths. For example, 19, if n is 5, then one permutation could be 19 4 1 2 5. It might not be the correct permutation, but it's a permutation of healths such that there is not a single winner. uh, for example, if n is 2 and I give both the participants a health of 1 and 1, right? So after the first round, both of the participants will have a health of 0 and both of them will lose. So at the end, after n iterations, it should not be the case that only one participant is remaining. Okay, so how do we do it? Let's look at it. So one thing you need to understand is the terminology of a threshold, which I'll be using. What do I mean by threshold? Um, for example, suppose you have initially n equals to 5, right? And you're at the first round. Threshold is that value V such that any participant who has a health less than or equal to V will lose in that round itself. For example, if n equals to 5 in the initial first round, the threshold is n minus 1, that is 4. Why? Because if there is a participant whose health is 3 or 4 or 1 or 2, anything which is less than 4, he will lose in this round. Uh, and if he loses, then the number of participants in the next round will change, and the threshold will also change. Okay, so let's make a tree like structure and understand what I'm trying to say. Initially, like I said, the threshold will be always n minus 1, because everyone will get a damage of n minus 1. So if your health is less than equal to n minus 1, you will automatically lose in that round. Suppose in this round, A0 or A0 participants are there whose health is less than n minus 1. And that means A0 participants will lose after that particular round. Then we go to the next round. What is the new threshold if A0 participants have already left? See, the new number of players remaining in the arena is n minus A0. Let's make a remaining variable. That means that now there are n minus A0 participants remaining whose health is greater than n minus 1, at least. We know that. What will happen after this round? If a particular participant initially had a health of HI, after round 1 his health became HI minus n minus 1, and after this particular round his health would become HI minus n minus 1 minus the remaining elements, which is n minus A0 minus 1, because uh, we do a minus 1 because we are not inflicting damage on ourselves. So if any participant, if this value is less than or equal to 0, then you die. That means the threshold here is n minus 1 plus n minus a naught minus 1. Okay. Similarly, suppose after this round, there are A1 participants who are dying, and now the new remaining variable going the next round is n minus a naught minus a1. So what will be the new threshold now? It would be, now I'll just get to a formula. New threshold will always be equal to the previous threshold plus n minus 1 minus sum of participants who have died. So it could be n minus remaining. You can also write it as n minus remaining. Okay, or in this case it would be a naught plus a1. So it would, now the new threshold would be the previous threshold plus n minus 1 minus a naught minus a1. Why? Same logic. First round hi, next round hi minus n minus 1, their health becomes, after this round, their health becomes this, and in the next round, which is the round we are currently on, their health would be the old health minus, what are the new number of remaining participants? N minus a naught minus a1. So n minus a naught minus a1 minus 1. So this is a small recurrence for the threshold which you can use. So new threshold is previous threshold plus n minus 1 minus players who have died. Something like this. Now, okay, now now let's end the tree here. Assume that all of the players die in this round, like A2 players die, and A0 plus A1 plus A2 equals to N. That means there is no use of continuing the tree because everyone has died. So this is a good situation. Why? Because um, there is, what would have been a bad condition? A bad condition would have been if there is only one player who is going to the next round. That means A0 plus A1 plus A2 plus 1 would equals to N. That would have been a bad condition. But if we are not going to the next round with a single player and we are ending the round, then it's a good condition. So we basically want a tree which looks like this. Um, like A0, A1, A2 should be on the left hand side, and there should not be any round where the remaining players are 1. Okay. Now, uh, now we need to understand is what values can we change and what values are dependent on what values. Okay. So the thing is that we can change these values of A0, A1, A2. We can choose that. We can choose, okay, in the first round, maybe only 3 players are going to die, or only 1 player is going to die. Because we need to find permutations, right? Or only 2 players are going to die. If we choose A0, automatically the next threshold is fixed because threshold depends on what? The previous threshold. Initial threshold is always n minus 1. The next threshold depends on the previous threshold plus n minus 1 minus players who have died. And you're controlling these values of A0, A1 and A2. So you only need to control these values and the threshold is automatically dependent on that. Okay. Now let's take a small example with actual values. So things become more clear. Suppose n is equals to 19. Okay, you have 19 players and assume x is anything. Okay, don't worry about x. X is infinity. You don't have to worry about x right now. Initially, the threshold is going to be 18, which is 19 minus 1. Let's assume that in this round itself, 3 players die. That means out of the total healths, there are 3 players who have a health less than or equal to 18. Maybe some guy has a health 17, one has a health 15, one has a health 2. So all of these 3 will die. Everyone else will proceed to the next round. Now, how? Now we will try to find the permutation at this step only. And how can we do that? See, we have 19 elements. So 19, C3, we pick any 3, and each element can have a value between 1 and 18 because it has to be less than 18 and the minimum value is 1. So the range is, I think, total 18 elements itself. It would be 18 to the power 3. These are all the possible combinations at this step. Okay. Now let's go to the next level. The threshold changes. Like I said, threshold is previous threshold plus n minus 1, 18. I think minus those players who have died. N minus 1 minus the players who have died. So minus 3. Okay. Now what does the new threshold becomes? It becomes 36 minus 8. It is 33. The calculation might be a little wrong, but that's fine. Now assume in this round 10 players die. What does that mean? That means that in that particular permutation, there exist 10 elements who have a value between 19 and 33. So this is the range for that, for these 10 elements. Why 19? Because every player who has a health less than equal to 18 has already died. So there are only players who have a health 19 or more, and the upper bound is 33. So if a player has health 33, he is going to die in this round. So 19 minus 33 is 15. So the range is basically 15 discrete values you have to pick. So the total, what is the total ways to do that? Well, you had how many elements do you have at how many people are remaining at this position? 16, because 3 have already died. So it would be 16C10 into 15 to the power 10. Okay, so these are total permutations at this level. Now let's assume that, okay, now the final level, it would be, the new threshold would be previous threshold plus n minus 1 minus players who have died, 13, right? It would be 19 minus 1 minus 13. Yes, that is 5 plus 33, 38. New threshold is 38. Let's assume, okay, at this level everyone dies. So 3, 10, we have 13, 19 players. So 6 players are going to die. Let's assume that 3 ends here. So what's the range? Again, you can find the range. The range would be 33 plus 1, that is from 34 to 38. And you have to pick how many elements? You have to pick, you have only 6 elements remaining, so you have to pick 6 from 6, and the range is 5, so 5 to the power 6. You multiply all these 3 permutations, you take the mod. So that is the number of ways for this particular arrangement. Where does the role of x comes? Well, the role of x just comes in clipping. For example, if x was, let's assume 36, x was 36, upper bound is 36. So at this level, when you are taking the threshold as 38, well, the threshold cannot be 38, it has to be 36, right? The minimum of the threshold and x. So instead of 38, we would have done our calculations with 36. That's the role of x. It can be ignored for now. So we need to basically find all the ways in which we can vary these a0, a1 and a2 values. And if I change some a0, then my threshold will change. Then if I change some a1, then my threshold will change. So a brute force method is not feasible, because every time you suppose you change a naught, then you will have to construct a new term. So we will go with dp. Okay. So we'll try to create a dp, but what should be the states in a dp? Should it be a 3 state dp or a 2 state dp? So let's think about it. See, whenever you are at a particular state, whenever you are at a particular state or at a particular level or a particular round, you need to know what is the threshold at that particular round. Okay. You also need to know how many elements are remaining, because you can only choose from those elements, right? And then you would have to loop over all the particular values of AI. That means AI could be 0, that is no player is dying at this round, one player is dying at this round, or every player is dying at this round. Once you find AI, you also need to know the range. So the range, the upper bound for the range is the threshold itself. But how do you calculate the lower bound? To know the lower bound, you have to know the threshold at the previous round. So you also need to know the previous threshold. So the threshold is basically the previous threshold plus 1 till this value. And the previous threshold was 5 and this threshold is 7. So you can only take the value 6 and 7, right? You cannot take 5 because those people would have died. You can only take values which are greater than 5 and less than equal to 7. So you need to know three things. So one thing which comes to our mind is maybe we can take a three-state DP, which would contain the threshold, the previous threshold, and the number of players who are remaining. You can, instead of taking remaining, you can also take the sum of players who have died. So A naught plus A1 plus AI minus 1. All the players who have died previously. So you can also take the sum because remaining is basically n minus sum. So both of the values are, it's the same thing. But this won't, I think, work because you have uh, uh, n equals to 500, right? So this would at least have 500, and the threshold can be, I think, greater than 500. Um, it won't exceed too much, but it can be greater than 500. So it might, I don't think it will work, but we just need to look at this idea and think about which thing can we get rid of. Okay, can we get rid of this term, can we get this rid of this term, or can we get rid of this term? Okay, so remember that previous recurrence which I told you about, which is new threshold is equals to the previous threshold plus n minus 1 minus sum. So you can see that the previous threshold can be calculated using these two values, right? So this previous threshold term is redundant. We can just have a two-state DP. So what we will have is we will have a DP of threshold and the total sum of this. Basically, sum basically means the players who have died. What are the total players who have died? Why did I call it as sum? Because it was equals to a naught plus a1, that is number of players who died in the 0th round, number of players who died in the first round, till all the rounds preceding this particular round. This was sum, that's why I called it sum. You can think of it as the number of players who have died. How will you solve it? Very simple. The first base case you need to handle is what will happen if the first thing you do is when you have to solve this particular DP, you calculate the number of remaining players first. The remaining players is n minus sum. Okay. If the number of remaining players is 0, that means okay, that's a good thing because you can just return DP of whatever equals 1 because we are completed. We don't need to do anything else. So if remaining equals to 0, then do this. Return DP of threshold sum equals to 1. If remaining equals to 1, which was a bad case, we don't want any round where there is only one person. So return this DP as 0. Okay. Otherwise, what to do is you iterate over all values of A naught. So for that, you have to find the range. The range would be the threshold, sorry for bad writing, minus the previous threshold. You can calculate the previous threshold like I told you. And then all you have to do is you have to iterate for I in range 0 to range. For I in range 0 to remaining. That means how many players are going to die at this particular level. So you calculate, okay, if I players are dying, then how can we formulate it? It would be remaining Ci into the range to the power I. Okay. So at this particular level, you will calculate this term. You will multiply it with dp of. So see, when you have decided, okay, I players are going to die, then you are going to calculate the next stage dp. That means I players have died, so the sum is going to change. Sum will become sum plus I, and the new threshold you can also calculate by the same formula. It would be threshold plus n minus 1 minus new sum, which is sum plus I. So you can calculate the new threshold. Basically, you'll call a function to find this dp, and combine these two things will be added to dp of threshold comma sum. dp of threshold comma sum plus equals to this value which you have calculated. Now there is now comes the edge case of x. I did not consider x at all right now. So where does x comes in? X comes in two places. Okay, the case of x comes, I think, in two places. The first case is when you are trying to calculate the range. The range was threshold minus previous threshold. Okay, but suppose the threshold comes out to be 38. That means any player who has a health less than 38 is going to die at this round. The previous threshold was 27, let's assume, but the value of x is 34. So this threshold will not be 38. Since it is greater than 34, it will become 34. Why? Because you cannot pick any element which has a value of 35 or 36 or 37, because the maximum health is 34 itself, right? So you will have to do a clipping here. You have to do it as minimum of x comma threshold. This is the first thing whether you are going to use it. The second is, suppose, now I'm not really sure if this state occurs or not, but I just add it for safety purposes. So suppose your current threshold is something, okay, and your previous threshold was also something. If the previous threshold is greater than or equal to x, then you will return 0. What does this mean? See, initially I did those checks. If the number of remaining elements are 0, then I return 1. If the number of remaining elements are 1, then I return 0. But now I know, okay, the number of remaining elements is greater than 1. I have done those checks before. I also know that my previous threshold value is greater than equal to x. That means now I cannot take, like, if I want to have, like, suppose if I have two elements remaining, their values can their values have to be greater than x, but which is not possible. Suppose the previous threshold was 38, the threshold is 38 also. Like x is 38 as well, and this new threshold, it can be anything. Suppose this is 39. So elements have to lie in the range of 38 plus 1 and 39, which is greater than x. That is not possible because the maximum value of x is 30. Like, you cannot exceed the health more than x. So you have to return 0. In that case, those are the only two edge cases, and so this is the entire algorithm. I'll just show you my code. Okay, so here's where I solve the DP. I have the threshold and I have the sum. I calculate the remaining elements. If the threshold is, like, if the DP state is already calculated, this is minimization. If the remaining elements are 0, that means we are done. We return it as 1. If the remaining elements are 1, which is a bad case, we return a value 0. We calculate the previous threshold, like I told you. If the previous threshold is greater than or equal to x, we return 0, which was an edge case, which I handled. Now I find the range, I apply the clipping. Now I go from 0 to the remaining elements, which are the number of elements who are going to die. Okay. So this is basically, suppose I pick p elements, and how many ways can I pick their values. So it would be range to the power p. This is like you can ignore this. Yeah, I also took a fail safe of what will I do if the range is 0. If the range is 0, that means again I'm not sure if that will happen or not. If the previous threshold and the new threshold are same, um, but in that case also, like this first term I've taken as 1. Um, then like this is basically me calling the DP for the next state. So if I pick p elements, then and no, I've also multiplied that with NCR. So this is basically just me writing bad code, but uh, it's something like NCR, like remaining CP into this p to range to the power p into calling the solver function for the next step. So in the next step, the threshold changes, the total number of people who have died changes, and I add that to my current DP, and then I return. This was an edge case which I had to handle. For example, if um, mm, like if the sum plus p value is equals to n. For example, if I am at the last stage, if I am at the last stage, and suppose I have 6 elements, right? So I am basically threshold mein I am adding n minus 1 minus sum plus p. If this value is n, so we are adding a minus 1. So I was not sure if, because n minus 1 minus n would become minus 1. I'm not sure if the threshold would basically decrease, and I'm not sure if that's supposed to happen. But since we will be ending at this step because we would have consumed all of the elements, I don't need to call the DP again. So this is basically me handling that case, that if we end at this level, if we have used all of our elements, we don't need to call our next DP because there will be no elements in the next DP state. But I don't think that this will matter at all, because yeah, it won't matter, I think, because we would return. Yeah, it's fine. We don't even need this if else statement. And then we return the current DP value. Uh, Also, like the size of, what will be the size of the DP? Well, since the second term, the DP of the sum value will have uh, value at most 500, because there are at most 500 elements, and only the number of n elements can only die, so its max value will be 500. For the threshold, like I don't have an exact value in mind, but see, I yeah, so for the threshold, like if assume that there are n, if there are 500 people in the beginning, so in the next round the threshold will be, you're at most adding something like 500 to the next in the next iteration, but it won't, and every element's health can also be at most 500. So if the threshold, if the number of elements are high, if n is a very large value, I don't think it's going to consume a lot of rounds before it converges. So that's why like I picked 500 into 4 as a decent value. And like you can also think about what should be the optimal value of threshold, but I don't have a clear cut approach for that. Um, Thank you for watching. That's all for this video. Bye.